Hello and welcome back. So we'll continue our discussion on frequency analysis, and this is the second part of the lecture on frequency analysis. In the last class, I talked about basic concepts related to probability, what probability is, and how do we define probability using probability density function and cumulative distribution function. So we'll continue that discussion today. Our lecture here is actually split into three parts. So in part A, I'm going to go over fitting empirical distribution functions. And in lecture part B of this lecture and part C of this lecture, I'm going to look at discrete and continuous distributions. So the lecture objectives are basically to see how we can use sample data or the data that we have collected or observed and fit an empirical cumulative distribution function to it. Okay, and we'll also look at, so this process of obtaining a cumulative distribution function from sample data is also known as plotting position, or we make use of plotting position formulas. And so I'm going to talk about some common plotting position formulas that we use in hydrology. And then finally, I'm going to illustrate the use of plotting position formula in hydrology using a simple R script. Again, you will use this R script and perform the same calculations in your class. So with that, let's delve in and look at these concepts. So what is an empirical cumulative distribution function? So the empirical distribution is an attempt to construct cumulative distribution from the available data. Again, remember that we're always interested about the population and not the sample. But we want to use the data that we collected or our sample and create a distribution function from that sample to describe the cumulative distribution function of our population. So the sample is a small subset of all possible things that can happen, or all possible values a random variable can take. And so we want to account for that, and we want to do that using the sample that we have observed or the measurements that we have made. So two things to remember is we need a way to project our sample data to scale up to the larger population or to infer something about the population from which this data came from, and also account for the possibility that there will be values in population that are outside the range of our observation. So unless we have performed a census and measured every possible value a random variable can take, it's safe to assume that our sample range may only be is a smaller subset, so our population range will be larger than our sample range. So somehow, when we construct this empirical CDF, we need to factor this in. So again, empirical CDF is developed using observed data. Must account for the fact that the observed data will not contain the entire range of variability of the population. So to calculate empirical cumulative distribution function, what we need is we need to find a way to calculate the probability or the cumulative probability corresponding to every value of our sample. Okay, and the way we do that is we use what's called as a plotting position formula or a plotting formula. And as you can see, there are several formulas that are available in the literature. Again, this list is not exhaustive. There are actually even more formulas than that. And the plotting position formulas all use two parameters. One, they use I, which is the rank. So if I have a set of observations, I can sort them from the smallest value to the largest value, and of course the rank of the smallest value will be 1, and the rank of the largest value will be equal to the length of your sample size, or n. Okay, so there are times when two samples may be the same, in which case you have to find a way to set a rank. One typical way to do it would be to take the two ranks and then split them and then skip a rank. So again, plotting formulas give us the y-axis of our cumulative distribution function. The y-axis, if you remember from the cumulative distribution function, has the cumulative probabilities, and this value here, depending on which formula you pick, provides that cumulative probability for some value of flow or precipitation or whatever our hydrologic variable of interest is. So we first take that variable, take the sample data, rank it, and then we get I, and then we get N, which is your sample size, and then you plug it into the formula to get your cumulative distribution function. If you notice here, most formulas, what are they doing? If you look at the denominator, they take your sample size. So the sample size is always on the denominator. This is the number of samples that we have, and they're adding some number to it. So in other words, they're saying that this is a way of making your population this is a way of expanding out of your sample into that realm of population. So you say I've collected N, but in reality there are more than N samples in my population. So one way to do it is to so what the product position formula does is it somehow adds a number that expands the realm of possibility. So that's one thing you see. And if you look at the rank, that it's always being subtracted. Some number is being subtracted from that rank. And that also follows logically. So it's saying, like, if I had a known sample size, this is the rank. But in reality, if I have a much bigger range, it's very likely that the rank is going to be smaller than what I typically see. So what the plotting positions all do is they take the rank and subtract some number, a fraction out of it, and then they take the denominator has the length, and then they take the length and add a fraction to it to kind of increase the sample size. Of course, the only exception is the California plotting position formula, which just takes the rank and the sample size. So California plotting position formula is is useful when you have a very, very large sample size, because if this N is very, very large, adding a small number will not make much difference to it. So if your sample size is very close to your population, California plotting position formula would work. Otherwise, we would go and pick one of these plotting position formulas. So that's what plotting position formula entails. So what's a plotting position? I've been using this word plotting position too many times. So a plotting position in statistics is defined as a set of ordered quantities and a list of fractions. So for a given set of ordered quantities, what we do is find a corresponding fraction of values at or below which the quantity is known as the plotting position. So essentially what it is it's an empirical cumulative distribution function when data are ordered in ascending orders. Okay, so plotting position formulas give us a way to compute the probabilities from ranks of the data points that we have, and these probabilities or the correspond to, or the cumulative probabilities correspond to every sample data point that we have in that sample. Plotting positions sometimes are also used with data ordered in descending order. This is useful to not find the cumulative probability, but 1 minus that cumulative probability, which is the exceedance probability. So in flood control studies and in floodies, we're interested in not low flows but in high flows. So we tend to use exceedance probabilities, and there are plotting position formulas for that as well. But in general, you get a cumulative distribution function. Getting exceedance probability is just 1 minus that cumulative distribution function. So how do we plot empirical CDF using plotting position formula? You take the sample data and count the number of observations. That's your N. And then you assign a rank to each data point. Okay, so if the data were to be assigned in ordered in ascending order, then the rank of the lowest value is equal to 1. So this is the rank I in this formulas. Okay. Select an appropriate plotting position formula. How do we go about doing that? Of course, is a big question and a very important question. So I'm going to discuss that idea at length in the next few slides. And then once we have the I and once we have the N, we simply plug it into the plotting position formula that we have picked and calculate the F, or the cumulative density distribution function corresponding to each of the quantile or each of the value that you have in your system. So what about values in the middle? Of course, you can interpolate the plotting position formulas, so to calculate the intermediate probabilities associated with it. Um, So one of the limitations of plotting position formulas is that you cannot calculate a value outside the range of your limit. So it does scale down the probability and it says that there is a good chance that you are seeing values outside your range. But it doesn't give us a way to go and calculate a value or extrapolate out to the side of the range. So one of the limitations, the big limitations of plotting position formula is that you cannot extrapolate this formula. You can interpolate, but you cannot extrapolate. So which plotting position to select? So if you know the theoretical distribution that fits the data well, again, in the next lecture, I'm going to talk about theoretical distributions. But for now, let's say we know our data is coming from a normal, follows normal distribution or follows that bell curve. If we know that, then plotting position formula is probably inappropriate. If we know that we are modeling something at extremes like peak flows or low flows, Green-Gordon plotting position formula tends to work well in that case. If you have log normally distributed data, the Hazen or the Hazen probability distribution function works well. There's also people who have recommended, or researchers who have recommended, that the Weibull distribution is fundamentally related to cumulative probability and return period. So it again depends on what we pick. Really depends on, we might have observed, we may not have had a theoretical distribution done for our site, but there might be another tributary close by. There could be another watershed that has very similar characteristics to the watershed we are studying in, and then we can say, hey, the flows there followed Weibull distribution, so I'm going to use Weibull distribution. So that's one way to come about it. And of course, if you don't have that, then one thing to do would be to try out multiple plotting position formulas and see what values we get. Typically, you will get a big range of variability between these formulas. Even though the numbers only vary in fraction, they do make a big difference in terms of probabilities, because you're looking at you're looking at the 0 to 1 range. Okay. Of course, if all the plotting positions are giving you fairly similar value, it really doesn't matter which plotting position you pick. But if they're giving widely varying values, then you have to decide which one to pick. And that, to some degree, or that will control how much factor of safety you're building into the system. So you might have a plotting position formula that says that a flow of 1,000 CFS could be a 100-year flood, and there could be a plotting position formula that says the Q of 1,000 CFS is actually a 10-year flood. And of course, so depending on how conservative you want to be, you would pick one of those two plotting position formulas. A lot of times, either state agencies like TxDOT or others give some recommendations, based on previous studies, based on what they have observed in the field. They'll come out and say, well, if you want to design this structure, we recommend that you take this data and use this plotting position, because we know that this plotting position has worked well for us in this area. So always make sure that if you have documents like that, do use them, because they're not put out lightly. They do look at data from several locations and then come back and say this might be a good plotting position versus this might be a good plotting position. So make use of those documentations. So why are we calling this plotting positions? Well, back in the day, we used to have what are called printed probability papers for various distributions. So you would have a normal distribution paper, a log normal distribution paper, a Weibull distribution paper. And what you would do essentially is take your data. You had to do a few manipulations to it, but once you got the data in the format that you would plot them essentially on this probability paper. And if that probability paper, if the plot gave us a straight line, then that was the distribution we picked. So the idea is you took your data, your sample data, and then plotted it on a probability paper, and performed the plotting position formula, and then plotted it on the probability paper. And that would tell us, if you got a straight line, that was likely the distribution that you wanted to use. So, for example, if I had a Weibull plotting probability paper, and I fit my data to the Weibull plotting position, and then I plotted them as y and x, then what I would see is a straight line. If I took the same data and plotted it on a normal distribution paper or a log normal distribution paper, it would come out looking curved, which would tell us that it's not from this distribution. So that's the genesis, or that's the idea behind probability distribution functions. Of course, we can do all of this in R or any statistical package these days. So nobody really has to go and buy plotting position papers and do this by hand. We have kind of automated this whole analysis process. But nonetheless, the plotting position name stays, and those are the formulas that we still use, that we used back in the day. So to kind of get you an idea of what plotting positions do and what plotting positions look like, let's do a simple or an illustrative example. The example is actually rooted in real world, and the example looks at data from the Blanco River, which is a river that flows in central Texas. And Blanco is a very famous river. A lot of people kayak there or float in that river, and so there's a lot of camping that goes on around that area. So in the Blanco River watershed. So in recent times, in 2015, there was a major flash flooding event that happened right around the Memorial Day. This, I think, was May 25th. So we had a huge flooding event, and as you know, Blanco River is in Texas Hill Country, so there were unusually high rainfall that year, particularly in the early part of May, that saturated the soils. And because the soils were saturated, when the second bout of rainfall came in and around Memorial Day, there was no place for that water to infiltrate, or there was very little capacity left in the soil to absorb that water. So the water started running down, and of course we are in hill country, so we have a little bit of an elevation gradient, or the maximum amount of elevation gradient that we typically have in Texas. And that caused the water to flow fairly quickly, resulting in flash flood situations. So ironically, Texas, even though is relatively flat, it's not very mountainous. It is one of the one of the states that has the most number of flash floods. The reason for that is our soils and our rainfall patterns. We just get very high intensity rainfall events, which just run off, and our soils, absorb water and saturate very quickly. So we have very low infiltration capacity, which is, the prime recipe for flooding events happening, such as the one in Blanco River. And Memorial Day flood, incidentally, was also one of those flooding events where people extensively made use of social media, Facebook, Twitter, to warn people about flooding. And this was one of the first cases where NASA and NOAA actually used Twitter. NOAA actually, and the National Weather Service, actually used Twitter to tell people that they need to evacuate and they need to get out. And the other thing about Blanco River watershed, about this flood, is that this flood actually destroyed the gauging stations on the Blanco River. So a lot of flow rates, or the peak flow rates that we have here, are just estimates based on looking at the river or looking at the videos of those rivers. So if you are interested in learning more about Blanco River flood, there are several videos. If you go into YouTube and type Blanco River flood, you will see several YouTube videos where people have gone back and videoed or surveyed what had happened after the flood. But what we are interested in is, we can actually go to USGS gauging station on Blanco River. The website address I show there. Otherwise, you can go to Google and just type in Blanco River USGS gauging station. It'll pop up, and you can go there. And if you go to USGS, station, you get different types of data. One data that you get is a peak flow. The peak flow is the maximum flow that was recorded at that station in a given year. Um, in 2015, the recorded peak flow at Wimberley, the Blanco River near Wimberley, was 175,000 CFS. Okay, so what we want to do is we want to use Green-Gorton plotting position because we are interested in extreme values, and we know that Green-Gorton plotting position works well with extreme values. And we want to calculate the exceedance probability. As I said, the exceedance probability is 1 minus the cumulative distribution function of flow being less than or equal to 175,000. So, which is nothing but 1 minus F 175,000. So we use plotting position formula to get this F or this P. And once we have that cumulative probability, then we do 1 minus that cumulative probability, and that will give us the exceedance probability. Okay. And once we have that exceedance probability, so the exceedance probability basically is the probability of my flow rate Q at that gauging station to be greater than 175,000 CFS. Okay, so climate change projections, particularly in Central Texas. Central Texas is a climate hotspot. And what they're saying there is that the rainfall is going to become more erratic. It's not that we're going to get more rainfall or less rainfall. We get the same amount, but we are going to get them in very different ways. So there will be a good chance, or there is a good chance that our flow rates or our flooding flow rates are going to increase. So we want to get a baseline of, say, what was exceedance probability in around 2019 based on the data that we had, and how would that exceedance probability change over time. Of course, we also know that that kind of flow rate, 175,000 CFS, literally caused a significant amount of damage, including death of life, including death of few people. So we want to know, what is the likelihood, if things were to stay the same, how likely is it, that we see this type of flooding events? Of course, these are rare events. We don't have 175,000 CFS in Blanco River every day. If we had it, our geography would look very different. So what we are really interested in is, on average, how long will it take for that type of flood, for us to see that type of flood. So the return period is what gives us that information, and the return period is nothing but 1 over the exceedance probability. So which is, we first calculate the cumulative distribution function, or the cumulative probability F. 1 minus F gives us the exceedance probability, and 1 over the exceedance probability will give us the return period. So that's how we calculate return period. And what does this return period mean? The return period doesn't mean that it'll exactly come back. And let's say the return period was 10 years. It doesn't mean that this flood will again happen in 10 years from now, or the flood happens once every 10 years. But it's more an estimate of saying, okay, so if we had 100 years, if you look at flow rates from 100 years, we are likely to see this flood about 10 times. So since the return period is 10 years, it means that it takes, we will see this type of flood 10 times during a 10-year period. So similarly, if I had a 500-year flood, then that is a much bigger flood, and the 500-year flood would basically mean, it doesn't mean that the 500-year flood would only come once every 500 years. It actually means that if I had 5,000 years worth of stream flow, I am going to see a flood of that magnitude or higher about 10 times. Okay, so it doesn't mean that it only comes once every 500 years. What it means is that there is a good chance, or there is some finite probability that it might come much faster than that. Okay, so it's very possible to see 2 500-year floods within a 10-year period. Okay, as a matter of fact, when we had Hurricane Katrina and Hurricane Wilma both hit New Orleans, it actually created two 500-year floods within the same year. So very small probability of that happening, but nonetheless, in our generation, in our lifetimes, we have seen two 500-year floods come and inundate a city within the span of a few months. So the return period, very important to keep in mind, is that is not a measure of you know the periodicity, or I'm going to get a rainfall of that magnitude or higher every 100 years. What again it means is that well, if I had 100 years worth of data or 1,000 years worth of data, what would it look like? And it goes back to that frequentist probability discussion that we had in our last class, where I said, again, what these probabilities, when we count and then get our relative frequencies and call them probabilities, what they are representing are a long-term average. Okay, so frequentist probabilities are long-term averages. So on average, in the long term, we will see these types of flood happening once every 500 years. That doesn't mean that the likelihood of such floods happening, more than one flood happening within a given year or within, less than 500 years is it still exists. Okay, somewhat of a difficult concept to grasp your head around when someone is just showing you some text and lecturing on it. But once you make those calculations, you start to see the importance of this calculation and what it actually means. But the key takeaway is that 500-year floods does not mean that the floods will only happen once every 500 years. So that's, or 10-year flood, the same story with any flood of any given year. Okay, so that is the key takeaway. And also, a 10-year flood is going to be a smaller flood than a 100-year flood, which is going to be a smaller flood than a 500-year flood. So as the years tend to go up, our magnitude of our flow rate also goes up. A couple of things about return return period. This is one of the classic outcomes, or for hydrology. So we will come back and revisit this topic again. Okay. So if we want to solve this problem, we want to take the memorial flood, we want to take this peak flow data. The first step you need to do is, of course, calculate, go to this website and select peak flow and download all the peak flow data. And what I show here on the left is the data that I got. Of course, I changed the names. See that there are no spaces, but this is the gauge height, or the height of the water column at that station, and then peak flow is the flow in cubic feet per second, or CFS, corresponding, that was measured. And in hydrology, we use October 1st as our starting date. So October 1st to September 30th is our hydrologic year. And so what USGS gives its data is, it gives its data based on hydrologic year. And if you notice here, in 1965, so the 1965 hydrologic year goes from October 1965 to September 1966, and they got a high flow of 16,500 there. 1966, still see the calendar date is 1965, but since it's after October 1st, it's part of the next hydrologic year, or the 1966 hydrologic year. And again, that has a flow associated with it. So it could be the same calendar year, but they could have different hydrologic years. So the peak flow estimates that are given to you are based on hydrologic years, not on calendar years. So this is the code. Again, on the top we have a little preamble. Always good to make some notes up there to say, what is this script supposed to do. Always good to put your name or whoever wrote that script, because especially if you share scripts in an office, having your name there helps, because somebody can say, hey, I know who wrote this script. I'll go and ask them what that script does. Okay, so that's one good way of, so it's always good to document your name as you write these scripts, and also put some notes as what this script does. So essentially there are 5 parts to the script that that we use for performing this empirical cumulative distribution function and calculating the return period. So the first step is to write a function for that Green-Gorton plotting position. So in R, we write Green-Gorton, which is the name of our function, and it takes a time series of flow, or like, and flow rate values like the ones that I'm showing in this column. So we supply that function with these values, and then the function goes and first sorts those values. This is not really necessary, but it makes plotting easier, so I'm going to do it here. And the I gives us the rank. If I don't, and that's how I calculate the rank. Then I go back and use this formula I minus 0.4 divided by n plus O2. So I have to calculate n, which is the length of my record. So I'll just count how many flow rates I have, and that will give me the n. And then I gives me the rank, and then the CDF is nothing but I minus 0.44 divided by n plus 0.12. And I'm going to take the Q that I have, which I just sorted, and the corresponding CDF, bind them into one group, and then what this function does is it returns it back to our main program. And what is our main program? The main program is, we first set our working directory. This is the directory where our all our files, particularly this file, resides. Okay, and then notice I have to use double backslash. This is a quirk in R, so you have to use double, because backslash is an escape character, so you need to use double backslash to represent your subfolders or the directory, or the path. Okay, and then you use the read.csv function, which basically takes a CSV file or the comma separated value file and reads it. And then $a peak flow, remember this is the peak flow here, and $a peak flow gives you that flow rate. Okay, and once I have that, I can calculate the CDF of Q using the Green-Gorton plotting position formula function that I wrote. And once I get that, the next step is to take the Q and the CDF that has been coming out of Green-Gorton, and remember we stored that in CDF-Q. So the first column is my values of Q, which is right here, and the second column is the cumulative distribution function, or the values of the probability. So I plot this, and then I beautify it by labeling my x-axis, labeling my y-axis, and then I plot a line to connect those things. And I also put a vertical line at 175,000 CFS. This is our design flow, or the flow of interest to us. And then I put a title on my part. So this is what this portion of the part does. And then R also has a function called approx, which you can use to approximate values. So once I have plotted peak flows on the x-axis, corresponding probabilities on the y-axis, what that approximate function says is, okay, now I know some flow. I'll just go up the chart and then find out what the corresponding probability is, and that's what this does, and that gives us all the information that we need. So in 5 steps and few lines of code, 20-30 lines of code, you're able to make this plotting position formulas. Now, if you want to do this at another station, it's a lot easier to do it with R, because you can make another file and call it, because not all gauging stations have the same record. So if I had this in Excel, and if I wanted to do, I have to recode all my formulas all over again, because there's no easy way for it to do it in Excel. So again, get into the habit of R. It's not that this calculations cannot be done in Excel, but having a little script will save you a lot of times if you have to do these calculations over and over again. So the results, it looks like this. This is my empirical plotting position. See, it's going all the way till that 175,000, which is the maximum value that we have seen. So this is my empirical cumulative distribution functions. Here are the cumulative probabilities. They go from 0 to 1, and here's the flow rates associated with it. This is like 50,000, 100,000, and 150,000 CFS. And if you notice, most of our flows, about 80% of our flows, are much smaller than our peak flow of 175,000 that we have seen. But there are instances when we are going to get more than that. Okay, we get more than that. So if I run that code, it gives me that the P of Q less than or equal to 175,000 is 0.9937. And what this means is that given our observed record, uh, the flow of 175,000 has not been exceeded 99.37 times. Okay, so 99.37% of the times the observed, not just the observed, but the population stream flows are less than 175,000. If you notice that my value of 175,000, which is the maximum value that I have in my record, uh, actually has a probability of less than 1. The reason is the plotting position formulas are compensating and saying, yeah, you have seen 175,000, but there's a good chance you will likely see a flood bigger than that. So you have not sampled, and there could be times when the flood was probably bigger, or there'll be times in the future when the flood is probably bigger. So that kind of tells us that um, it's so that's what it's saying. So the maximum in your sample. So if I were to just look at my sample, I would conclude that 100% of the time, my flows would be less than or equal to 175,000 because that's all I have. But I want to take that and take my empirical cumulative distribution function and extrapolate into population, extrapolate in accounting for the fact that, yeah, I have just observed 175,000 as my maximum flow, but it's possible that I can see a flow bigger than that. And that's what this plotting position formula does. So once we have that, we can use the approx function, and then we say, okay, what is the probability, right? So we've already calculated our cumulative distribution, or our cumulative probability, which is 0.9937. So 1 minus 0.9937 is 0.006463, and that is your exceedance probability. So the exceedance probability is 0.0063. So there's a very, very small chance that this flow will be exceeded. Nonetheless, if that flow were to exceed, then we are going to have a flood that's more devastating than what we saw with the 2015 Blanco River flood. We can also estimate the return period, and the return period is 1 over that exceedance probability, and that is approximately 160 years. So basically what that return period says is that there will be about 6 floods of this magnitude or higher in a 1,000-year period. So basically, if you look at a 1,000-year framework, you would see about 6 floods of this nature over that time. Okay? But that doesn't mean that you will see these floods coming in 160 year like clockwork every 160 years. It's very, very possible that the flow may be exceeded in 2 subsequent years. The flow may be exceeded in 2 subsequent months. So that's so we need to keep that in mind when we interpret return periods. To summarize, empirical cumulative distribution functions can be obtained using plotting position formulas. There are several in the literature to deal with different types of data. ECDF, or the empirical cumulative distribution function, is what we get by applying plotting position formulas to our data. And ECDF is important to get an idea of what that cumulative distribution function looks like. And also, if you want to quickly say, what is the probability of a threshold not being exceeded? What's the probability of flow being less than some number? Let's say I take the flow being less than 50,000. I simply go up the chart and then go here and say, okay, that's about like 0.85 or 0.87 is the probability. There's an 80% probability, or there's an 80% chance that the flow in Blanco River is going to be less than 50,000 CFS. Okay, but that small chance and a flood associated with that small chance causes significant devastation. So we always deal with very small amounts or very small exceedance probabilities, because that gives us less risk when we design our structures. So one idea is to kind of get a quick and dirty or like an initial idea of what our CDF or the cumulative density function looks like, distribution function looks like. And then the biggest use for empirical cumulative distribution functions is to actually fit theoretical model to data and see how well that fit is. Okay, more on that later. We're going to spend some time in the next class doing that. And also you can use empirical CDF to get a quick idea of what that return period is. And that is useful before you start fitting models and spending time. You just have a good idea of what that number looks like based on one of those empirical distribution functions we have. So that's the lecture on empirical cumulative distribution functions. In the next class, we will talk about theoretical models or models that we can fit to calculate our empirical, to calculate our theoretical distribution function. So statisticians have developed theoretical distribution functions to model various types of random variables or the various types of phenomena that are represented by those random variables. So I'm going to go in and talk about a few that are most relevant to hydrology and most commonly used in hydrology. So that's what's coming. Where we were initially talking about probability and saying that probability is best characterized using the probability density function or the empirical or using the cumulative distribution function. And in this class, what we did was we looked at how to plot that cumulative distribution function given some data that we have. Again, the cumulative distribution function that we plot using plotting positions, or the empirical cumulative distribution function as we call it, is not really a distribution for the sample. It is a distribution of the population from which that sample came. Okay, so that distinction is very, very important. So again, I showed you an illustrative example using R. What I recommend is that you take that code and you take that data and play with it, perhaps write a function or modify the function I have to include Canaan or to include Hazen, and then see what it does to the return periods. Like, so what does it do to return periods? What does it do to the cumulative flows? So you can play with that, play with this code that I just gave you. All right. So that concludes this lecture. And in the next lecture, I'm going to talk about theoretical distributions.